Okay, so we are going to be looking at the second half of chapter 11, which deals with chains. And just as this very same function was the same for belts, chains are designed, or chain drives are designed to transmit rotational motion and torque from one shaft to another in a smooth, quiet, and inexpensive way. Now, chain drives are kind of a combination of both belts and gears, meaning they have belt characteristics in that the center distance is nice and flexible because we can kind of go further apart or closer as we need to. But it has the positive transmitting characteristics of a gear because gear has teeth that actually physically push past each other. So chains are going to have sprockets that actually move the chain past, where belts do that by design, they slip if there's any overload situation. Now, as we look at chains, they are considered a low-cost item. They are readily available, mass-produced. They're made out of metal, so they're quite inexpensive to produce, and then also they're not very costly to buy. They provide no slippage. So in the case of belts, as we said earlier, if there becomes an overload situation, a belt will start to slip just because of the nature of not having the teeth to catch it. And that is by design, and that is used to protect maybe more expensive or more intricate and involved machine components downstream. Gears, or I'm sorry, chains on the other hand, don't slip. They're going to physically have those sprocket teeth go up in between the spaces on the chain, and they are then going to pull it along. So you do run a higher risk of jamming, overloading, and breaking other elements. Okay. They do have that flexible center distance. They're more effective at lower speeds. So as we saw with belts efficiency, their best speed for transmitting the loads and the forces was between 4,000 and 5,000 feet per minute when we looked at the belt speed. For chains, they can take care of those lower speed applications more effectively. So they have a wider range of effective transmission. So that's really nice about them. They do have a little bit of maintenance. Typically, you're going to have some sort of lubrication on a chain drive. It might not have to be that it's on a constant basis, but there is going to be some upkeep to extend the life of those components. And they do have a longer service life, chains do, than belts. And that's just the nature of being made out of metal. Now, chains can be made out of other materials, and we see that, of course, but predominantly for industrial applications, especially in mechanical world that we live in, just the regular run-of-the-mill steel roller chain is what's going to be seen most often. Now, let's look at some typical arrangements or types of chains. So I'm going to go underneath my camera here. And on page 308, where the chain section starts here, we have some illustrations of some configurations or types of chain that we have. Now, the most basic and most popular and most readily used is going to be our roller chain, which is very familiar to us. This is the type of chain that we're going to see on our bicycle, okay? And you're going to notice that it's made up of side plates. There's going to be a pin going through to connect to the other side. And then there's a roller around that pin. Okay, so a very, straightforward configuration here. Now, the second one that we have is really a reapplication of that roller chain, but now it is going to be ganged together for multiple strands. And you'll notice here that we have 3 strands wide. What this allows us to do is it allows us to have a lower profile chain, meaning we don't have to have bigger, chunkier chain, and we just add rows to it to increase the strength, okay? So we'll talk about strength of that, but multi-strand roller chain is quite common for industrial applications. Another one that we see here, and if you kind of look, instead of the side plates being straight, this is called an offset sidebar roller chain, used a lot where we are going to be maybe putting it together, taking it apart, and adding in and putting in different types of accessories for maybe automation or conveyor uses. And then lastly, we have the silent chain. And the silent chain is a quieter chain, and we see this typically. Well, actually, you tell me. I mean, by looking at it, can you think of an application where the silent chain is used, or have you seen that? Engines have them. Where else do you see them? Anybody? Anybody ever see this kind? Escalators and escalators. These are the types of chains that they utilize. So that's the one that comes to mind for me. So so those are a couple different types. We are going to be focusing on the single strand roller chain, which gets us again a lot of mileage, especially in you know, the kinematics of things. Chain pitch, okay? Chain pitch. Now, just like for gear teeth, we had diametral pitch and we had pitch diameter. We have the same thing for chains, except we just call chain pitch, okay? And then we call pitch diameter on a sprocket the pitch diameter. So we got to keep those two straight here. So if we look at the roller chain up on, or the pitch, the chain pitch up on the top of page 309, I'm gonna go underneath here, and there's an illustration of a side plate, one single side plate on a roller chain. The pitch is going to be classified by the distance from one pin to the other. Now, to determine that distance, we're going to be calling chain out by numbers, okay? So if we turn the page, let me go to the bottom, there's a table on page 309. I'm sorry, 310. There's table 11.5. And these are commercially available single strand sprockets. Now, what I want you to note here is that the size of the chain here is considered a number, okay? So when we specify chain, it's by a number. Now, to get the conversion to the size or the distance between those two pins on a side plate, which then equates to the size of the pitch, we simply take the number of the chain and we divide it by 80. So, for instance, if we have a number 80 chain, to find the equivalent distance between those two pins or the size of the pitch, we take 80, the number of the chain, and we divide it by 80. So that means that's going to be 1 inch is going to be the dimension between those two holes on the side plate, okay? If we have something like that, you'll notice that if you go back, there's a number 40 chain. Number 40 chain, then, to get this dimension, we're going to divide by 80, and that would be a 1/2 inch pitch. So by that convention, the higher the number, the wider or the longer the pitch gets, okay? Now, additionally, and we'll look at sprockets in a little bit as well, when we specify our roller chain size by number, it's also going to come along with an accompanying size teeth on our sprocket, okay? So just like with gears, we had to have mating gears with the same diametral pitch in engagement with one another. We also need that very same thing going on here, where our chain number is going to correspond also to the size of the sprocket that we get to the teeth that are coming up, because they're going to be sized to go up in between those spaces, okay? So so that's chain pitch. We talked about 80 divided by 80. The larger the pitch, the greater the power carrying capabilities. So what we find is as these get wider apart, those pitches get wider, the side plates will get thicker, the pins will get larger. So the larger the number, the bigger, the chunkier the chain, the more force and the power carrying capability we get. Now, let's talk about multi-strand chain. So you are going to notice that we had looked at this illustration where we had, in this case, 3 rows of chain, okay? We can have a number of different rows. So if we go back to page 310 and up on the top here, we have this illustration or this table, and it says multi-strand factor. Now, if we have 2 roller chains, this is going to give us our multiplication factor, meaning if I find what the power is that I can carry for a certain size chain, okay? And it's usually going to be rated by horsepower. If I find that out and I then put, you know, another strand of chain next to it, I do not get a multiplier by a pure 2, okay, I get a multiplier in this case of 1.7. Okay, and the reason that is if we go back to the illustration where we had the multiple strands, what happens is some of those side plates are shared between the strands, okay? It's not a doubling effect of each one of the elements, unfortunately, okay? If it was, then we could probably say double the power carrying capability, but it just doesn't work that way. So the way that it's configured is some of those side plates are actually going to be shared between. So it's not a pure one-to-one relationship when we have multiple strands. We have to then use the multiplication factor here, 4, 2, 3, 4, and so on. Okay, so just be aware of that. I don't think anything that you're doing, you're going to be worrying about that, but it is a good point because you will be revisiting chain drives when you do machine design elements, and there you will see these number of strands come up in problems that you're potentially going to do. Okay. Okay. Sprockets, let's look at sprockets. We can see a sprocket on page 310, and the sprocket is going to be that toothed wheel that is going to go up in between the spaces of the chain, and it's going to basically pull it along. Those teeth on that sprocket are designed with geometry that's going to conform to the size of the chain that it's going to pair with. So going back over here, and as I stated earlier, our sprocket, we have to make sure that it is specifically made for the size or the chain number that we specify for the roller chain. So those two do go together. Let me go back over here. Pitch diameter. You'll notice that there is a pitch diameter on here, just like there is on gear teeth. So very similar. It's going to be that place where it engages with the roller chain, and that is where the torque and the power is going to be transmitted. Effective diameter. Think of it in terms of like a gear. So again, it's kind of a hybrid between a gear drive and a belt drive. Let me go back over here. Let's look at the geometry of a gear drive, and we're going to stick on this same illustration, and we're just going to move over to the right. So over on the right-hand side here, we see kind of a classic arrangement for a chain drive. Just like in other drives that we've looked at, the smaller sprocket is going to be on the faster moving shaft. So in this case, I would expect that this smaller shaft is going to be what we call our driver, just like we did for belt drives. And then the driven sprocket is going to be the larger one. So most often we're going to have this driver coming off of a motor, coming off of an engine, some sort of input of power and rotational speed. And then the output is going to go to whatever this is driving, whatever the machine is going to be, okay? Now, you're going to notice some nomenclature here that is going to be common from other things that we've seen. First of all, we've got rotational speed. Just as with belt drives, the rotational speed direction is going to be the same for both sprockets in this case, the way that this is arranged. You'll also notice that they use the numbers 1 and 2. 1 is going to be your driver. 2 is going to be your driven. Okay. Pitch diameter, small d, is going to be that physical diameter that is going to be that effective diameter on the teeth of our sprocket. Capital N is going to be the number of teeth on the sprocket. So just like with gears, if I wanted to figure out, for instance, what a velocity ratio is, I can count the teeth between the two, and I can figure that out. So N, capital N, is going to be number of teeth, and notice that is for 1. Then over on the right-hand side, you're going to see the very same items with the number 2. You will notice that we have this theta 1 and this theta 2. This is that angle of wrap, okay? So in this case, we want to make sure that there's at least 120 degrees of wrap, or I think they call it angle of contact, where we have engagement with the sprocket. If we don't have enough teeth and engagement, we're not going to be able to get the performance out of that drive that we're expecting. Now, again, in kinematics here, we're not so worried about like horsepower and torque. We will use it to size a belt in the problem that we're going to be looking at, but it kind of stops there in kinematics. We would continue with the design in machine design elements, and that's what you have coming up next term in spring 1. So there you are gonna get re-exposed to this and kind of finish the design, if you would, in that course. So we did pitch diameter. Oh, center distance. Center distance is going to be the distance between the driver and the driven. And just like there was for belt drives, we are going to have a range, and this is on page 311. We're going to have a range for which we have optimal performance. So 30 times the pitches. So whatever your pitch ends up being, okay, you're going to multiply that by 30, and that's going to be your low side of your center distance range. And then you multiply it by 50 to get the high side of the center distance range. And your center distance should land somewhere in between there. Okay. If you're a little bit out on one side or the other, not a big deal, but you want to use that as a gauge for, best performance. A couple additional equations that we're going to see here. As we look above that same equation, you're going to find that this is going to be and actually, you know what? Instead of just pointing to these, why don't we get out a piece of paper and we will devise and we'll start our chain drive equation sheet so that we have these in a place that's a little bit more handy for not only the problem that we're going to do, but for your assignments as well. So we're going to kind of work on this page a little bit, and we will get our chain drive equations. And we'll kind of walk through them so that we're ready to use them on our example. Now, this is the pitch diameter one, but what I'm going to do is I'm going to add one on here because they don't put it in here. They talk about it in the text, but they don't specifically put it in here. So I'm going to do the chain pitch is going to be equal to the chain number divided by 80. Okay. And what that's going to give us is it's going to give us units of inches, if you would, per tooth. Okay. Inches per tooth. P is equal to chain pitch. So chain pitch is going to be specified by a number, but to calculate what the numeric value is for the physical size of the chain, or the physical size of, if you would, the side plate between those two holes, you're going to, express it in inches per tooth or teeth, okay? And again, that P goes back to this illustration right here, okay? The pitch is going to be a dimension, but it's actually called out as a number. And then again, we divide by 80 to get what that corresponding dimension would be, what that distance between those two pins. Then the next equation we're going to put here is going to be the pitch diameter. So lowercase d is going to be equal to our pitch divided by sine times 180 degrees divided by the number of teeth, okay? So over here, this is going to equal pitch diameter of our sprocket. And that is going to be in inches, okay? And then N is going to be equal to the number of teeth on, the sprocket that we're looking at. Now, as far as units, okay, we're going to notice that on top, our pitch here is going to be those units of inches per, I'm going to say per tooth, I guess, because it's really for an individual, divided by, now this is going to be 1 over teeth, okay? So tooth and teeth, because this is considered one, I think it's kind of weird to say inches per teeth. These teeth and tooth are going to cancel one another out, okay? So you'll notice that the units that are left over are inches for pitch diameter. So that makes sense, okay? All right, so that's the first one. Then I do want to put this, center distance range. So this is going to be range of center distance. And our C is going to be in the middle. and it needs to be greater than 30 times whatever your pitch is, but less than 50 times your pitch, okay? And C is equal to center distance. Now, when we do our problems, especially if we're not given a center distance that we're dealing with, we pick a center distance to start off with, and we use that center distance to calculate the length of the chain. And the length of the chain is going to be given in links. Okay, that's what L is. It's not going to be in inches, it's going to be in links, because when we get roller chain, for instance, off of a bulk roll, we literally count the links, and it has to be an integer number. Okay, so what we're going to do is we're going to pick a center distance, okay, within the range that's acceptable for the pitch size. And we're going to use it to determine what are the number of links in the overall length of our chain that's going to fit around. So when we talk about the length of the chain, it's how long this has to be to fit over both of those sprockets and obtain the center distance that we desire. Okay, so I am going to write down this equation here. Now I'm going to kind of do it down below. So capital L is going to be links, and then 2 times C is center distance divided by P. P is going to be our pitch diameter, plus N2 plus N1 divided by 2, plus, and then in parentheses, it's going to be pitch times N2 minus N1, and we're going to square that quantity divided by 4 times pi squared times the center distance. Okay, so it's that whole equation right there. An easy one to forget, because I get caught on it once in a while, is going to be squaring that pi value. Okay. The next equation we want to write down is going to be then, once we get our links. Now, once we get the number of links, we're probably going to calculate it, and it's going to be a decimal value. So what we're going to do is we're going to choose an integer number. Is it integer or integer? Integer. Yep, number. And it needs to be even. Okay. That's just one of the requirements. I believe that the reason you want it to be even is because that way, as it rotates around, it doesn't go on the same chain all the time. Like the same tooth doesn't hit the same chain, like in between each time. So even and an integer number. So if we get something like, I think we end up later, we get like 137.2. We wouldn't round down to 137. We would go up to 138 because it's an even integer number. Okay. So that's going to be what we get. And then what we do is once we know what the number of links are, okay, we are then going to find our actual center distance, okay? And that equation is right here. It's pretty long, so I'm going to zoom in here in case you don't have your book. I want to make sure that you can see it, and I'm going to write it down here. Be careful to write it in the correct form. There's a lot going on here. So C actual, I'm not going to read this all out for you, but you want to get it on your equation sheet. For those who had, actually most of you, I don't think all of you, but most of you, a lot of you had me for computer programming, and we did a chain design spreadsheet. And if you recall, there was a really long equation, and because of this, it's these two guys. You will again revisit this in your machine elements class next term. You get to do it again. I'm gonna let you in on a little bit of a treat. For those of you who, I have to believe at this point, you're pretty okay with putting units on things. But this is the exception that I have for this particular assignment. When you use these two equations for the length in links and your center distance, I do not require you to put all your units in for these because it would like get way too long. Like even I can't write it. So it's easier just to put the numbers in and then go with it. So just so you know, that's going to be my exception. These two, you don't have to put the units in when you write them out. So you will get a break on that for these just because it gets really long. If you want to put them in, go ahead, no problem. But I'm not going to require it because it does get to be kind of messy. So that's our actual center distance. So again, we would pick on a design in our range. We would base our number of links on that center distance, that trial center distance. We would find then the integer even number of links based on that equation. And then now we're going to use that down here to get our actual center distance. This would be the final, if you would. Okay. And then the next two that we see here, this is going to be the angle of wrap, okay, or angle of contact. Theta 1 is going to be for our driver. Theta 2 is going to be for the driven. So if we look over here, theta 1 is on the left-hand side, theta 2 is on the right-hand side. And as it states here, we want to make sure that we're always greater than 120 degrees. So you're going to want to write down those two as well. So we've got theta 1, 180 minus 2 times the inverse sine times P times N2 minus N1 divided by 2C. And it's a very similar equation, except this time it's going to be 180 plus 2 inverse sine times P times N2 minus N1 divided by 2C. Okay. And then I just put a little note on the side here, need to be greater than 120 degrees. Now there's just two more equations we're going to be adding, and those are going to be the kinematic equations as they're referred to. So up on the next column here, this is where we have our velocity ratio options. And these look familiar. Notice that for chain drives, because we have sprockets that have teeth on them, we now can figure out our ratio using and counting the number of teeth on the pinion and the gear. Okay, remember, velocity ratio is going to be trying to figure out how many times that driver has to go around the smaller sprocket in this case to get the driven to go around just once. I'm sorry, I just saw this. Oh, thank God. I bet that was in reference to the units, right, Josh? Yeah. All right. So we're going to want to write down all of these options here for velocity ratio. So we're going to see that familiar W1. So remember, ones are the drivers and the twos are the drivens. And then twos go on top for the physical sizes and the teeth, because the twos are going to be the higher number for that. Yeah. Okay. And then once you have that down, then we want to add in this case, it's going to be the chain speed. So this is, if we look back and we remember back from when we looked at velocity ratios the very first time, this is the straight line velocity component of a rotating element. Then when we were looking at gears, this was the pitch line speed. And then when we were looking at belts, this was the belt speed. And now we're having it in terms of the chain speed. So I'm going to add a note or two here. So this is going to be chain speed is going to be equal to pitch diameter divided by 2. Now, if we're dealing with the driver, this would be the pitch diameter, number 1, times its angular velocity of that same sprocket, okay? And we can also say it would also be equal to the pitch diameter of the driven times the angular velocity of the driven. Now, this value right here is going to end up being in feet per minute. Those, just like a belt speed, feet per minute is the most common units that they're going to be in. So that means when we do our angular velocity, we are not going to use RPMs. We're going to use radians per minute, because otherwise, if we do radians per second, then we're going to end up reconverting it back into minutes for the final units. And then the diameter, we're probably going to have in inches to start off with, and then we're just going to have to do a quick conversion to feet at the very end. Okay. So, so these, with a number of these being kind of familiar to us, are going to be, if you would, a very close reapplication of things that we've seen already. Okay. So any questions on the equations? I know they're not spread out all over, but it is nice to kind of just get them written in the format that we like, as well as gives us an idea of what they mean. Now, on the subject of the kinematics and the pitch, or the chain speed here, once we calculate our chain speed in feet per minute, we are then going to qualify it in either being low, moderate, or a high speed drive. And what that does for us is it lets us know what is the type of lubrication that we need to design into it. So for instance, if we have a chain speed of less than 650 feet per minute, it's considered low speed, and you just have to manually lubricate it, kind of like on our bike, right? You don't have drip lubrication or a bath lubrication on our bike. We just occasionally go in and we lubricate it manually. But if we get up into moderate and high speeds, this is where we're going to have to then consider designing in one of these options here. This is going to be a bath lubrication. That's where part of it actually goes through a bath, and it kind of you know, brings that lubrication around as it goes. But then there's also for high speed where it's actually an oil or a drip lubrication that is constantly on there as it's running. So, so a couple different ways or schemes that you're going to have to consider down the line on the design. But it's important to just kind of be able to understand and know where you're at with your chain speed and how that affects lubrication. Okay. So I think let's go back to our PowerPoint. I think we're going to be ready to look at this last example in this chapter. Yep, we just talked about velocity ratio. So we're going to be looking at example 11.3. Okay. Example 11.3, the statement is found at the bottom of page 311, but the illustration, if we turn the page, is going to be up at the top of page 312. Okay. So we've got a chain drive for a chipper shredder, and it's going to be coming off of an engine. Our drive is going to be down here. So this is going to be our W1. And then our W2 is going to be the driven machine, the chipper shredder thing is going to be our W2. Okay. And we are going to be designing the chain drive for this element. So if we go back to and look at in detail the problem statement, then we can kind of see, you know, how we're going to proceed or what we're going to be looking for. So you'll notice here it says a single strand roller chain drive connects a 10 horsepower engine to a lawn waste chipper shredder, as shown, which we just looked at. As the engine operates at 1200 RPMs, the shredding teeth should rotate at 240 RPMs. The drive sprocket has 18 teeth. Determine the appropriate pitch of the chain, the number of teeth on the driven sprocket, the pitch diameters on both of the sprockets, and the chain speed. Also indicate the number of links in a suitable chain and specify the required center distance. Okay, so we've got a lot going on here. So what I want you to do is I want you, just like we have in the past, kind of start out with, this is example 11.3, and this is the last of our practice problems for module 6. Okay. So I want you to list from that problem statement, what is the information that you're given? And what is the information or what are the elements that you need to try to find? Okay. So go ahead and list using this description and variables that you know are going to be what you're looking for. Okay. And I'll kind of do this on the side here as well. And then we will compare. Okay, so as we look at the problem statement, it told us that the engine is going to produce 10 horsepower. So we're just going to kind of put that in there as a placeholder because we're going to need it to pick the size of the pitch that we're going to be using, the chain pitch. We know that the engine is running at 1200 RPM and that the chipper shredder needs to run at 240 RPMs. Number of teeth on the driver is 18. And then the items that we need to find are listed over here. So P is going to be our chain pitch. Number of teeth on our driven sprocket. The pitch diameters of both the driven and the driver sprockets. The chain speed itself, straight line velocity. And then the length and links of the chain to go over the top of both of those sprockets, as well as the center distance that we are expecting, okay? So I got a little bit of work to do here. And actually, it's really nice because besides the angle of wrap, we really are going to be using almost all the equations that we looked at on our equation sheet, okay? So as we look, we'll follow this example along and because their process is good. Their process is good. So where they started was they wanted to select the appropriate chain pitch, and they have selected 40 pitch, but let's make sure that we know and understand why they came up with 40. Okay. So we're going to look at figure 1110, which we did not really reference when we went through things. So let's look at figure 1110 that is found at the bottom of page 309, and you're going to see this chart. Okay. Now, what this chart does is just kind of like, it does the same thing we looked at it for diametral pitch for gears. We looked at it for a similar type for belts. And now it's going to help us to come up with what is the size of the chain that we should be using for this application. Okay, it's like, where are we starting here? So the bottom axis here is going to be the speed of the small sprocket in RPMs. So the speed of the small sprocket, which is our driver, is going to be 1200 RPM. So it's going to be this line going up, okay? And then we're going to match it up with, now you got to look at the top here. This says number of strands, okay? We're going to be one strand. So it's the one that's closest to the y-axis here. And this is going to be the horsepower. So over here it says the units of horsepower. So we're going to go up to 10 and we're going to go over to 1200, okay? And it intersects right there, okay? Now it lands in the 40 chain area. Now this is where, as a designer, okay, it's really kind of up to you. You'll notice that if we would go up just a little bit more, we would be on the number 50 chain. Hold on. Do we assume it's one strand unless otherwise specified? Correct. I think this one did say single strand, actually right in the beginning of the problem, single strand, but you are correct. Yes, you would assume single strand. All the ones that you're doing for this assignment in kinematics is single strand, but in machine elements, you will be experiencing some multiple strands. Okay, so now in this case, now we are going to go with what the book says. The book picked 40 because it landed within the 40. As I look at the placement or where it landed in the 40, it's kind of almost to 50. I would probably go with 50, but you as the designer would have a couple other things to consider. Maybe, I mean, these are just some things to think about if you would be out in industry. You would want to look, okay, number 40 chain, I'm kind of on the edge. How volatile is the application? You know, what are the chances of it jamming and such? I don't know. When I see a chipper, an industrial chipper, I think that's kind of great. Okay, so I would probably go up with this. We're gonna stick with 40. Another one would be, do we have any of these that are in stock or we get a good price on it because we buy a lot of it? Then you might pick 40 over 50 or 50 over 40 for that reason. So there are things that you would consider outside of just where does it land here. Okay. So as a designer and as we're following the book, we're going to go with 40, but I think there would be a good case for a 50 here if you wanted to. Okay. So you'll notice that they decided on a 40 pitch. So what I'm going to do here as my step number 1, okay, the pitch is going to be 40, okay? And that is from figure 1110 or 1110. Yeah, 1110, not 1010, 1110. Yes. Now, this means that our pitch is going to be 40 divided by 80, and that is going to be 0.5 inches per tooth. Okay, that's going to be our overall pitch. Okay, that's going to be that this is ½ inch between those two pins on that side plate. Okay, and when we call out the pitch for our chain, the units for it are going to be inches per tooth or inch per teeth, if you would. Okay, because it equates to a physical size as well. Not only it's going to be a number 40 chain, but it equates to a pitch of a ½ inch. Okay. All right, so knowing that we are going with a number 40 chain and that we have 18 teeth on our driver, we now need to figure out what are the number of teeth on our driven sprocket. So we did our pitch of our chain. Now, number 2 is going to be determining what the number of teeth on our driven sprocket is going to be. So if we go back to our equation sheet, down here in our velocity ratio helps us with that. Okay, so here's our N2. We know N1, and we're going to set it equal to the ratio of the driver speed to the driven speed. We know that the driver is at 1200 RPM, and we know that we need to accomplish 240 RPM for our output. Okay, so we're going to set this up so that we have W1 over W2 is going to be equal to the number of teeth in our driven sprocket divided by the number of teeth in our driver sprocket. So solving for the number of teeth on our driven sprocket, we would get N1 times W1 divided by W2 is equal to N2. And I would basically say this is going to be 18 teeth times 1200 RPMs divided by 240 RPMs. RPMs cancel, and I'm left with teeth for my units. And we should get N2 equals 90 teeth. Okay. Now, we do need to pick and make sure that these are available commercially for the sprocket for a number 40 chain. So we need to go to table 11.5 down here. Okay, I'm going to zoom in here. This is the commercially available single strand sprockets. Okay, so it looks just like the one that's above here. Now, if we go to the number 40 chain, it's going to list out the options on that row. So it says 8 through 60. So that means for every integer between 8 and 60, they make a sprocket. All right, that's what it's telling us here. And then after 60, it's not quite as consistent, but there is a 90 tooth sprocket. So we would have an 18 tooth, which would qualify between that 8 and 60, and then 90 gets us to the 240. Okay, so it's perfect. That means that we can confirm that the number of teeth on our driven sprocket, we can put a box around this, is going to be 90. Okay, because again, it's listed, I'll put on there, this is from table 11.5. Okay. If number 90 wasn't there, then you'd have to, do an iteration. All right, but it was. So now we can go back up here and we can say number of teeth in 2 is done. Now we need to calculate the pitch diameters for the driver and the driven. So this is going to be number 3. And we do have an equation for the pitch diameter, and that is going to be here. So D is going to be equal to our pitch, but that's going to be in inches. Don't put number 40 up here. You're going to put a ½ inch or 0.5, okay? And then under here is going to be the number of teeth for the corresponding sprocket that we want to do. So D1, for instance, is going to be equal to P over sine of 180 degrees divided by N1. So that's going to be 0.5 on top, and that's going to be inches per, it's really inches per tooth, but teeth and tooth are going to cancel out each other. And then it's going to be sine times 180 degrees divided by the number of teeth, which is going to be 90 teeth. Okay. So teeth and teeth cancel, and we're left with inches. So my D1 about the chat box. I want to be sure we're getting these numbers. Okay. So you should get a diameter, and this is a good time to make sure that you're doing these calculations properly on your calculator, that you get these numbers, because they're not as, this one's not bad, but especially when we get to the links and the lengths and the center distance equations, they get a little bit more complicated. Oh, no problem. Have a good night. Happy Thanksgiving, Christian. Okay. All right. So now, did everybody get 2.88 or 2.879? I think the book lists 2.88, which is correct. Okay. Now we're going to do that very same equation, but we're going to do it for D2. So I'm going to turn this over. My D2 is going to be equal to my pitch again, divided by the sine times 180 divided by this time N2, because I'm looking for the pitch diameter of my driven sprocket. So this is still going to be 0.5 inches per tooth. Okay. Divided by sine times 180 degrees divided by 90 teeth. Oh, wait, did I put the wrong one in there? I did. This was supposed to be 18. I was like, wait a second. Sorry. So if you did use 90, hopefully you didn't, because I needed N1. N1 was 18. Our N2 is 90. So 90 goes here. And D2, it looks like, Josh, you got 14.327. Absolutely. That sounds correct. And make sure everybody can get that one. Good. Yeah, 90 for this one. That's N2, 18 for the previous one. Okay. So those two pitch diameters we have, so we can cross off these two. So we've got just a couple more to go. Our next one is going to be our belt speed. Okay, our belt speed. So we do have an equation for that. If you recall, that was actually the last one that we wrote. Okay, our belt speed is going to be the radius of our sprocket pitch diameter times the rotational speed of that sprocket. Okay, and again, we have to use radians per minute because we want to end up with feet per minute as our final units. So this is going to be step number 4. We're going to use the belts, or the chain speed is going to be equal to D1 divided by 2. Now, the reason I'm using D1 is because original information, we have W1 and we were given the number of teeth. So the chances of our diameter being correct, I'm quite confident in D2, but it just has a little bit more, if you would, more original information. And then this is going to be times W1. Now, as we said, W1, our angular velocity, has to be in radians per minute. So on the side here, I'm going to say W1 is equal to 1200 revolutions per minute. And I just need to convert that to radians per minute. So 1 revolution on the bottom, 2 pi radians on the top. Revolutions cancel. So our W1 should end up being about 7539.6 radians per minute. Okay. And then that'll be the value that we put in here. Okay. So our D1 was 2.879 inches. We're going to divide that by 2 times this number right here, 7539.6 radians per minute. Oh, I'm kind of sneaking in here. Okay. So my belt speed is going to be 10,853.3 inches per minute. Okay. It's going to be inches times radians. So radians magically disappears, right? This is comma. And then we are going to change it to feet per minute. All right. Make sure when you're handing in your work, check the answer key for the units that the final answer is in. So for chain speed, the accepted units are going to be feet per minute. So we want to put it in those accepted units. So that means we're going to divide by 12 because there's 12 inches in 1 foot. Inches cancel here. So I'll be in feet per minute. So my final chain speed should be 904, and you can put FPM. Okay. Make sure you can get those numbers. Okay, and that makes sense. And what's nice is this straight line velocity equation for the chain speed. It's a reapplication of things that we've been doing for a couple of modules here, which is nice. All right, any questions at this point for anything that we've done so far? Okay. All right. So if we go back to the beginning here, we have our belt speed done, right? Now we've got to tackle the number of links for the length of chain that we would do. So again, we're going to be specifying in the number of links for a chain that is going to fit over the top of our sprockets. I actually can, we have a thing here. So we want, how long is that chain and in how many links it actually is, okay? So, so what we're going to do is we're going to use that links equation or that length equation. Now, when we look here, we look at this equation right here. We know the number of teeth in each one of our sprockets. We know the pitch that we have for the sprockets, but we don't know the center distance. And this is where we're going to figure out what is the range of the center distance I have to be in based on the physical size of the pitch of my chain. And then I'm going to pick a number within those boundaries. Okay. So if I go here, step number 5. Okay. I need to pick a center distance. So I know that my center distance needs to be greater than 30 pitches, but less than 50 pitches. Now my pitch in inches, we are not going to put 40 here. We're putting in the inch equivalent, the distance equivalent. So this is going to be 30 times 0.5 inches, right? And then it's going to be 50 times 0.5 inches. So pretty easy to do in our heads. This is going to be 15 inches and 25 inches. So our center distance needs to be between those two numbers. So what the book did is they picked 20, okay? So if we look at our example, we are down at step number 5 here. They did the 15 to 25. And then when we look at the top of the next page here, it says a mid value is 20 inches. So they're just picking as our trial center distance, okay, C is going to be 20 inches, all right? Not our final center distance, but the one that we're going to use to figure out how many links do we need to determine or to get over the top of our sprockets. So step number 6 here now is going to be calculating the number of links that we need to obtain the center distance of 20 inches, okay? So what you're going to do is you're going to write out your equation here and then fill in your numbers. So go ahead and do that. And I will do that on the side here as well. Now, remember, you have to write out the equation in variable form first, okay? But then when we do this equation, you do not need to put the units in. It's just too, it's just too crazy. It's just a little too crazy. And I'm quite confident, and I know that it's all going to come out. Don't forget to square pi in that final quantity there. Okay. That is so easily forgotten. So let's scooch this up here a little bit. So this is going to equal 2 times 20. And then for P, you want to put the 0.5, the inch equivalent to. Don't put 40 in for P in calculations. Always use the distance. So I'll give you a chance to make sure, and this is one of those places where having the answer in the book is important because we have the ability to, kind of check our answers. Oh, I just noticed something that I didn't mention in here because we didn't reference back to the book. I am going to let you know, and this is going back to step number 4. There is an error in the book. This is a misprint. Their radians per minute for W1 is incorrect. Okay, ours is correct, which then they use that number to calculate it. So your final feet per minute is not 1300, it's 904. Okay, so if you do go back and actually compare to the book, we didn't do that. I apologize for not doing that. The book is incorrect just in this one step. Everything else here looks good. It's just in the one step. Okay. So I'm hoping everybody got, or something really, really super close, 137.28 links using the numbers that are there. James is a good, yep, the book has that as well. And so now this is where, if you recall from our equation sheet, we said the links need to be an integer number and it needs to be an even number. So instead of going down to 137, because that's an odd number, our links, we're going to specify 138 links for our length. Okay. So we would pull off physically 138 links. Okay. So we're going to round it to the nearest integer, but an even number. Okay. So it looks like they got that very same number here, but then as it says, we want an even number of links. 138 links is going to be specified. So now that we know exactly how many links we have, now what we want to do is we want to recalculate and get our actual center distance based on the 138 links. Okay, so that's going to be the last step that we take here. So our last step, which is, I think, step number 7, is going to be our center distance. Our center distance actual is going to be equal to, so again, make sure that you're doing, that you're writing it out exactly the way you see it here. This is going to be P over 4. And you're going to multiply that by, I'm not going to read this all to you. You guys can rewrite this. Now, oh, I think I already mentioned that. To be your equation. I'm going to put my numbers in. Kind of broke it into like down here, these are just kind of the different elements and what they were. So if you're doing it in different stages, you can kind of make sure that your numbers match up if you're not getting the right answer. But here, just be careful with your squares, your square roots. Don't forget to square the pi. I forgot that like twice. It's not one that we square very often. And again, a great opportunity to just make sure that you know how to, get all the numbers so that it matches. And the book's answer for this one is correct. All right. Looks like in the room, we've completed the equation. It's good. Okay, how about virtually? Everybody get the same number? 20.19, 20.187. Okay. So that takes us then to the end of this problem. So the last two things that we still needed to calculate were L and C. Okay. So this is going to mimic, we kind of touched almost everything. We didn't do angle of wrap, but that's kind of a plug and chug. I'm confident that you guys can figure out what is the angle of wrap based on the information that we have here when called upon. But this example is going to mimic the last assignment problem that you have for the chains. Okay. So any questions right now on chains? Because I've really gone over information wise and example wise what I wanted to. All four aren't like this. No, they aren't. No, they aren't. Only one. Only one. The last one. Okay, so let's take a peek at what's there. All right. So the first four were belt related. The last four are going to be chain related. So on page 314 in the second column, the first problem you're going to work on is going to be problem 1118. Here we have a gear motor operating clockwise at 225 RPMs is coupled with a number 40 chain. So it's giving you that to a liquid agitator. The drive sprocket has 19 teeth and the sprocket on the mixer, which would be the driven sprocket, has 50 teeth. Determine the speed of the driven sprocket, so W2, the chain speed, VC, And then the recommended lubrication method. Now, once you get your VC, you will compare to at the bottom of the column on page 311. Okay, so right above problem 11 or example problem 11.3, we looked at these low, moderate, and high speed. Once you determine how fast your VC is, you want to qualify it as low, moderate, or high, and then say, is it a manual lubrication, a bath, or an oil stream? Okay, that's all for that one. Then your next one, I think, is very similar, where you've got a shaft on a gearbox, is coupled with a number 100 chain, rotating a drive shaft for a pulp screen at a paper producing plant. The screen drive shaft rotates at 250 RPMs clockwise. The drive sprocket is 25 teeth, and the mixer sprocket, or the driven, is going to be 76. Determine the speed of the sprocket, W1, and of the drive sprocket, and the chain speed, VC. And then also, what is the recommended lubrication based on slow, moderate, or high speed? All right, so those two are very similar. The next one that you have is going to be 1122, 2 sprockets, number 80 chain, 19 and 64 teeth. The chain has 140 links, so you already know how long that is. Determine the pitch diameter of each one of the sprockets, their center distance, and the angle of contact over the smaller sprocket. Also compare the center distance to the ideal range. So what you're going to do is you're going to determine what that ideal range is, and then let me know, are you in the ideal range or not? Okay, so some way relay that information. And then the very last problem is going to be like the one we just did. So just one of these, that's going to be 1126, the chain drive desired for a corn picker to couple hydraulic motor with a drive shaft. The 300 or the 30, not 300, 330 horsepower motor will operate at 550 RPMs, and the drive shaft must operate at 100 RPMs or close to 100 RPMs as possible. So it doesn't have to be exact, all right, but they want you to select appropriate commercially available sprockets. So this is where you are going to reference this chart right here, okay? Once you pick your chain size, your sprockets are going to be then listed on the row. So that's what we checked with our 18 and our 90 on the last example. You'll be picking your set, okay? Because this time they're not giving you the number of teeth on the driver sprocket. Select an appropriate size, commercially available sprockets, and the number of links for the chain. Also calculate the actual chain speed and the center distance. So this one is just like example problem 11.3. Okay, so you've got a good example there, you know, to go through this process. So any questions on these last 4 problems or anything from module 6? Okay. If not, then I'm going to stop the recording here.